This is a review of the lab of a weak acid strong base titration. In this lecture, I'll be showing you how to identify all the necessary components of this informal lab. And I want to stress for those that are chiming in and looking and listening and seeing that this is a non-equilibrium type lecture. So we will stay away from equilibrium type problems until later in the course. So this is just basically a stoichiometry version of the titration. Okay, so what do we have here? So let's think about what's going on. Well, in this lab, okay, what I have is a weak acid base equilibrium. Or I should say a weak acid strong base titration. There will be a weak acid base equilibrium that occurs. Yes, that's important. So let's consider what happens here. So in this lab, what we have in a beaker, we have 25 milliliters of a acid, and this is a weak acid. That acid was acetic acid. The acetate ion is C2H3O2. It's -1, H in front, now it's the acid. This is vinegar. And we had an unknown concentration, so a question mark molarity, but we had 25 milliliters. In a burette, okay, with the standard solution, this is the solution that we know of, okay, we had a 0.03 molar solution of calcium hydroxide. Okay, now this is the standard solution, and sometimes we would call this the titrant, okay? So we would say, and it's important to understand these word problems, that we're titrating this acid with this standard solution that we know of. Titration means you're using a known amount of the standard solution that's verified to get the unknown concentration. All right, so what we're doing is we have a beaker of, let's say, HA. That's my weak acid. And we know that it doesn't dissociate very much, so most of it's HA. There is some H, A minuses and H pluses. And what we're doing is we're adding drops. This is my drop of hydroxide, a strong base. Okay. We're also making sure that we understand that we're using a dibasic base here, so there has to be some considerations when we try to figure out this concentration. Now, the key to this weak acid and strong base, I guess I should put acid here, so weak acid strong base titration, is that we want to find the equivalence point. This is the point where I've added enough of these hydroxides to make all of the HAs go away. And let's consider what's happening here. Let's go right to the net ion equation, because that's important to know what's going on here. So I'm going to white out some stuff here. Okay, so what I'm going to do is start with my acid. And as we can see, the acid is acetic acid, and we're going to understand that it's a weak acid, so very much there's a small amount of this acid that actually gets dissociated, okay? And because a small amount gets dissociated, we would say that it's a bad electrolyte and that it stays together. So I'm going to write in my net ion HC2H3O2. Because it's a weak acid and barely dissociates, breaks apart into H plus and the conjugate base, I write it this way. That's important. Now I'm adding calcium hydroxide, but that's a strong base. Strong bases, by definition, completely dissociate into the hydroxides, and in this case, 2 hydroxides, but a calcium plus 2. It's going to completely dissociate as long as my concentration of my group 2 ion is low, as we'll talk about later in the course. So I'm going to add some hydroxides. Now I know I'm adding 2 hydroxides, I know that, but for every 1 acid, there's 1 hydroxide that the calcium gives off. And what happens is I'm not going to add the calcium plus 2 because I know that it's going to spectate. The reason why calcium hydroxide, okay, is a strong base is because its conjugate base, so to speak, or conjugate acid, the calcium plus, if you want to consider that, has no ability to ionize water. In any case, it's going to spectate on both sides, so I don't edit. So what's really happening here? Just like we would do for a precipitation, let's just get to the bones of the problem. The hydroxide is going to pull this H, and what you're going to make is the water. All right, and then what's left over is the conjugate base, C2H3O2 negative. Notice the charges on one side equal the charges on the other, and this is the appropriate net ion equation. I do that because we want to see what's going on here, and that's what you have to do for one of your steps of the lab. Knowing this, we know that we're going to produce water by neutralizing this weak acid with this hydroxide, but the key to understanding this is that we're going to produce some conjugate base that has some ability to react with water. So if I white out some more here, let's see what it would do. Well, what it will do is this conjugate base that eventually gets reacted will react with water because that's the predominant species, and when it does so, it's this negative ion, this conjugate base is negative, will pull an H, reform the acid. That's the reason why it's a weak acid. The conjugate base is pretty strong, so it's going to reform the acid, but it's going to make OH minus. So what I'm going through all of this is to help you realize that we're going to make some OH minus here. And that means when we neutralize, okay, all of the weak acid and force it into its conjugate base, that conjugate base is then going to react with water to produce some more hydroxides. Therefore, the equivalence point will not be at 7 because the conjugate base has an ability to ionize water or react with water. If this was a strong acid, strong base titration, we would be dealing with a conjugate base that has no ability, and that's why the pH would be at 7. So because we're producing a conjugate base that has an ability to react with water, we're going to produce some extra hydroxides, and the pH will be above 7. Okay, that's important. So now I'm going to go after my equivalence point, because what I'm after here is the concentration of my acid here. So what I'm going to do is I'm going to go after my equivalence point. Now, graphically, the only way that I can get it is graphically, because I can't calculate it here because in this lecture we're staying with equilibrium problems. So, but graphically I can see that there's an exponential increase right around here, and there's an exponential kind of decrease here. And graphically I can measure kind of this difference from here to here, okay? And it's an estimate, but it looks like to me that this is the middle, about the middle of the asymptote. All right, so I'm starting here, going here, and it looks like to me, let's see here, 1, 2, 3, 1, 2, 3. Okay, if you think it's right around here, it's fine, but I'm going to make things easy for myself. Yeah, let's make it, it looks like to me it should be higher, so let's just deal with it there. Okay, so I'm going to say it's a little higher. So again, I'm estimating based on how these things are panning out, and it looks to me like the middle of the asymptote is a little above. Okay, so I'm going to do it right here. Okay, so this is my equivalence point. It's kind of the middle of the asymptote, and if I was to read this and go off to the left and read this graph, I've got a pH at equivalence point. If this is 5, 6, 7, I don't know, 8 point, let's say 3. Okay, this is 9, so 8.3 is my pH at the equivalence point. But that is a value above 7. That's the reason for that is the conjugate base we made. But that's not what I'm after. Okay, right now I'm after what that volume will be. So let's go get that volume. So I'm going to read the volume at the equivalence. Again, I'm estimating here, but these are good estimates. Okay, so it looks like I'm about right here. So 11, 12, 13, 14. Let's do 14.7. So 14.7 milliliters is the volume of the what? It's the volume of the base I had to add so that all of the hydroxides I added equal and match all of the weak acid. Remember, the weak acid doesn't dissociate well. That's why the initial pH is higher than if it was a strong acid. But we're matching the hydroxide. So at this position, we're saying all of the hydroxides are equal to all of the what? Weak acid I have. That's important. That's important. You got that. This is the equivalence point. All right, very important. It's the first thing we find when we look at a titration curve. Okay, so the equivalence point. So I'm going to take this 47 milliliters and I'm going to do something with it. So let's white out some area here. So what I'm going to do here is I'm going to figure out my initial concentration of my acid. That's one of the first things. So very simple. I have the volume it takes to neutralize. Now we're going to go and find the moles and then eventually the concentration of the acid. So how do I do that? All right, let's do it. So I'm going to take my point Christmas in July. Okay. All right, so back to this. So I'm going to take my 0.0147 liters. I'm converting this to liters. I'm going to times it by the molarity of my standard base solution, because this is the volume of base added. I'm going to times it by 0.03. This is moles per liter. It's a molarity. And you can see, party people, liters cancel. Okay, so let me go find that. And I take my calculator and I'm just converting for moles, something that we've done a lot in precipitation analysis. All right, so here we go. So I get a value to be 4.41 times 10 to the negative 4. And that's moles. Moles of what? Moles of my hydroxide. Well, wait a minute. Is it my hydroxide? It's really the moles of calcium hydroxide. And we learned that for one calcium hydroxide, there are 2 hydroxides. So what's the ratio? For every one, whatever the molarity of the calcium hydroxide is, the concentration of the hydroxide ion is going to be 2 times that because there's 2 hydroxides. So I found the concentration of the base, but the base has 2 what? Hydroxides. So I'm going to times this by 2. Okay, important you realize that. To get total hydroxides, I just found the moles of the base I added based on the concentration of the base that was given. But to get the number of hydroxides, I had to times by 2 there. So times by 2, and I get 8.82 times 10 to the negative 4, and that's moles of what? Hydroxide. What else is it? Well, it's also the moles of the H pluses that were neutralized from the weak base. All right? So to find, party people, the molarity of my solution, which we know is moles over liter, I'm going to take the moles of my H plus, which are the same as the OH minus. Hey, that's what this is all about. We found exactly that equivalence point. All right, so I'm going to take that moles, which is 8.82 times 10 to the negative 4, and that's moles over the concentration of the acid that I started with, right? Which is 25 milliliters. Okay, so because it has to be liters, 0.025 liters. Okay, so let's put this in our calculator. Divide by our moles by the volume in liters of the acid. And what we get is I get the molarity to be 0.035. And probably 35. We'll stop there for 2 sig figs based on the limiting factor, which is the 2 sig figs in the volume. okay? And that's equal to the concentration of the what? The acid, okay? This is this C, the H, C2H3O2, the acetic acid concentration. And that's one of the things you need to define, okay? So again, it all starts with the equivalence point. Let's go after the Ka. Now that I know the equivalence volume was 14.7 milliliters, that's exactly how much volume of the base at this concentration was needed to neutralize all the acid. Well, guess what, party people? Guess what? If I take that volume and I divide by 2, that's exactly the volume necessary to half neutralize. So this gives me 7.35 milliliters, and that represents the half equivalence point. Okay, 567.3, so something like that. And if I go all the way up, that's something like that. Okay, so that's the half equivalence point, which is important. I'm gonna write it half equivalence point. Some people would call this the max buffering region, but since we're staying away from equilibrium, I am doing max. We're gonna call this not max buffering, but we're gonna call this half equivalence. And that's really important to find. Why? Well, I know that there's something really special at this position when you're dealing with weak acid or weak base. And what's very special is that when you're at the half equivalence point, okay, what you have is you have the equal amounts of the conjugate acid and base. And let me explain. At this initial pH, okay, you have 100% of the acid. We'll just put HA here. All right? Let's assume it doesn't dissociate. And you have 0% about, anyway, very low percentage, of the conjugate base. At the equivalence point, you've driven off all of the acid into conjugate base because you dropped the OH minus on this. So all the OH minus that came from the burette reacted with the H plus, or was pulled off. And so you have at this point, okay, 0% HA left. That's gone. There's no more HA. That A, this H went with the what? Went with the hydroxide to make water. Okay, so this is 0% HA, and you have just made 100% your conjugate base, which we all know the conjugate base is this negative ion here. Okay, I'm writing as A negative to make things simple. So what's the half equivalence point? Well, the half equivalence point, you have 50%, okay, of your acid left because you neutralized half of it, and half of what you neutralized became the conjugate base. Again, if you don't know what's going on, look at the net ion. If we had a mole of this and we added a half a mole of this, wouldn't we produce a half a mole of this? Yeah. Okay. So funny. All right. So this is 50%. This is the halfway equivalence. Now, what's so important about this? Well, if you look at the Henderson-Hasselbalch equation, yes, it's a mouthful. pH equals the pKa plus the log of the conjugate base, that's the negative form, over the HA, that's the undissociated acid. We know at this position, my friends in chemistry, that these have to be equal amounts. And equal amount over equal amount means that this becomes the log of 1. And the log of 1 is equal to 0. So this goes to 0, and pH equals the pKa. Whoa! So what is this pH? Again, I'm just roughing this. So if this is 4, let's do 4.4. Okay, so I'm going to guess 4.4. So I've got a 4.4 pH is equal to the pKa. And how do I get from a pKa to a Ka? This little p means negative log. So this is an exponent. I want to bring it back to a real number. So what I'm going to do is do 10 to the negative 4.4. It's one of our requisite skills in acid-base kind of problems. I'm going to go from the exponent back to the number. What does that equal? Well, put in our calculator. 10 to the x, you're going to go negative 4 0.4. The reason why I put the negative is because it's negative log. That's what little p means. So to go backwards, it's 10 to the negative 4.4. And what I get, party people, is I get, let's change colors because I can, I get 3.98 times 10 to the negative 5. And that equals my Ka. pKa was the negative log of the Ka. The entire Ka is stuffed in an exponent at this position here. Has to be. Okay? So I just found the Ka of my acid. All right? And we have the concentration, the equivalence point, now the end point, okay, of this titration, since we used phenolphthalein, all right, would be somewhere in this region. We don't know for sure, but the end point for phenolphthalein, so let's just write it, the end point. Now we do know in a table of pKa's for phenolphthalein, it's about 9-ish. So the end point is probably in this region for phenolphthalein, using the pKa of phenolphthalein to be, I don't know, 9.3 or so. So that's where the end point was. And we always talk about the end point is the color change that occurs that tells us that we're about at the equivalence point. They're not the same. Very important. Okay. Now we've got all of that. I think what we have left to do is determine the percentage of the acid and base. We just did that. And I think all we've got left is to determine the final pH. So the final pH, we want to find this, and this is really a lot of fun here. I think so. And the reason is because the final pH just represents the excess chemical that we added beyond the what? Beyond the equivalence point. So if we looked at, we're at 14.7. So from this point, I'm magenta now, like that? Yeah. So from 25 to 4.7. So 25 minus 14.7 is going to give me the total amount, okay, of milliliters of base that was added. So 10.3 milliliters represents the extra what? The extra acid that was added. So I have 10.3 milliliters. We know that becomes 0.0103 liters of my extra acid. I'm sorry, base. I keep doing that. Base that was added. Remember, we kept adding base beyond that. So I know my initial concentration is 0.03. I'm going to find the total moles of my hydroxide. Keep in mind that I know it's it's calcium hydroxide. So there's twice the number of hydroxides. So I'm going to times this by 2, get the total number of hydroxides. So case in point, 0.0103 liters times the molarity, which is 0.03, gives me a moles equal to 3.09 times 10 to the negative 4. All right, now remember this is liters and this was mole over liter. That's why the liters cancel. Okay, great. So I added that many moles. Now we're trying to find what? We're trying to find the pH. Now, to know the pH, if I could find the pOH, which is the negative log of the what? Hydroxide concentration. See my line of thinking? I want to know what the concentration is, molarity of my hydroxide. Well, this is the mole of hydroxide. I'm going to divide by the liters of the entire solution. And make sure you understand something. The final pH meant in my beaker, I added 25 milliliters of what? Of strong base into a beaker that already had 25 milliliters. So the final volume of the solution is 0.050 liters. Okay, so we're going to divide by 0.05, and I get a concentration to be 0.00618, And that represents the concentration of my hydroxide. And what do I do from here? I'm going to do a negative log. That's going to do that, so I do negative log in my calculator. So negative log of my answer. And that gives me 2.2, let's say 1. And I'm going to subtract that by my kW, which is 14. So 14 minus this, and I get approximately, and I get 11.79, which is equal to my pH. And that's my final thing. Remember, kW is equal to the pH plus the pOH. Okay, so my pH is 11.79. And if we look here, this is 11, this is 12. 11.79 is what I got, but it's pretty darn close. Okay, so good estimate. So I hope that helped with that.